Okay, so now we get to the heart of the valence shell electron pair repulsion theory, which is going to give us the shapes of molecules. That's really important in understanding how they're going to react. So, essentially, VSEPR is based on the idea that electron pairs don't want to hang out together. So when you have one electron by itself, we know from Hund's rule that they're going to spread out in as many energy boxes as they can go into, while still pointing the same way as their neighbors. When you're talking about bonding electrons, so those were atomic concepts. When you talk about bonding electrons, those unpaired electrons have a tendency to want to match up with somebody. So one pointing up, one pointing down, because that gives them a lower energy state. Beyond that, so pairs of electrons are stable. Beyond that, though, if you tried to take another pair and get it close to the first pair, they're going to repel each other. They're going to try to stay as far away from each other as they can. All right? And so, in order to figure out how that concept impacts the shape of a molecule, we got to start by drawing a Lewis dot structure. You may need to think about resonance. You need to think about formal charge and try to find the best structure that you can come up with. You need to think about the octet rule and what exceptions are okay and not okay. Once you have a Lewis dot structure, we're going to be counting the number of bonding domains. So that's areas where electrons are in bonds around the center atom. We're also going to count non-bonding domains around the center atom. And then I have a chart that's going to be an easy, quick reference to figure out how the shape is related. I also think playing with this PhET simulation will help, so I just want to show you, and it will give us two different names. So when we're talking about shape, we're talking about geometry, which is names. We have two different kinds. We can think about where the molecule is organized, so that's molecular geometry, and we can think about where the electrons are organized. To start off with, let's just say I have just one bond between two atoms. So this might be like hydrochloric acid, for example. In this case, there is no center atom. There's no clear reason to pick purple or gray as your middle. That means counting domains doesn't really make any sense. There's only just one bond between these two things. And so no matter how I spin this, the shape is always the same. It's always a line between these two atoms. So when I only have two atoms, that geometry is always going to be linear because it makes a line. If I add another one, did you see what happened? So we started off with just the line here. And then when we added another one, it initially tried to go in on the top. And what happens? The other electron bond runs away. Look. It's trying to get away. It takes a second, but it tries to get as far away as it can. So if you have a center atom with two atoms attached, so we would call this two bonding domains, that is always also linear because the farthest apart they can get is 180 degrees. Now if we add a third bonding domain, we end up with a triangle. Right? So no matter how I flip this, it's always going to be a triangle. Try to get it close together and they run away really fast. Right? So this is a flat triangle. And so triangles have a bond angle of 120 degrees. Right? So this would lay flat on the table. If I add a fourth domain, this is one of the most stable shapes. Oh, I didn't even... Back to the triangle first before I move on. It's important to notice we don't just say triangle, we say trigonal planar. So it makes a triangle and it's flat. We're going to have other triangles in a little bit that aren't flat, so we have to say planar. Okay, so 4 bonding domains is one of the most stable that you can have. It's very common, especially for carbon. We call this shape tetrahedral. So a tetrahedron is something that people don't see very often, unless you're a gamer, or you know someone who is. So a tetrahedron, from a molecular perspective, a tetrahedron looks like this. So this is This is called methane. It's carbon in the middle and hydrogen's on the outside. So a tetrahedron is really interesting because it's really very symmetric in 3 different directions. I found one. Also, we rolled at 20. That's great. So this is a tetrahedron, all right? And so this is kind of the 3-dimensional shape of methane, where each point represents a hydrogen, and in the center of this dice we would have a carbon. They look like little pyramids, except that most pyramids have a square base and these are triangular bases. Okay, so that's what a tetrahedron is. And tetrahedrons, ideally, in a perfect world, are going to have a bond angle of 109.5. Okay, so a tetrahedron is the basis for a lot of our other shapes. So for example, if we actually have 3 bonding domains and 1 non-bonding domain, all right, it turns out, this is so much fun, you can move the bond angles around. You guys should play with this, it's fun. It turns out that in the real world, in the simulation, it's telling us the bond angle is 109.5 still, but in the real world, electrons occupy more space than bonded, unbonded electrons occupy more space than bonding electrons. So these bonds actually, so when we have non-bonding electrons, they actually occupy more space, which means these bonds in reality are going to be smaller. So one example of an atom of molecules that do this is ammonia, NH3. So in more or less realistic numbers, NH3, there's an H in the back, NH3 bond angles tend to be about 106 degrees according to MolView, okay, which is different than the predicted value of 109.5 because that lone pair of electrons, not shown here, but there's 2 unbonded electrons on the top here. They take up more space than the bonding electrons do, so it pushes the bonding electrons closer together. For our purposes, we'll say that anything with an electron geometry that's tetrahedral, so 4 domains, here we have 3 bonding, 1 non-bonding, that means the electrons are arranged as a tetrahedron. We'll say the bond angle will remain at 109.5. But in your future studies, it's important to understand that that is not a hard and fast rule. That's an estimate in a perfect world. And of course, the world is not perfect. The molecular shape does not match the electron geometry whenever we have non-bonding electrons. So we have these 2 non-bonding electrons up there. And so that means that the electrons are arranged in a tetrahedron, but the molecule looks like this, and it is not a tetrahedron. This is called trigonal pyramidal. So, or pyramidal, depending on your accent, depending on where you're from in the US. So trigonal pyramidal happens when the electrons, so this is my methane again, when the electrons are organized the same way as any tetrahedron, but you take off one of those atoms. So now, in the molecular shape, we're only able to look at the bottom part, which is a triangle. It's a pyramid, so trigonal pyramidal. And we call it that to differentiate it between trigonal planar, right? So here's a flat surface. If I put my molecule on here, you can see that it does not touch the bottom, the black part of my tablet here. Trigonal planar would, so they would have to be pushed down like this. Oh, that takes a lot of force, actually. So trigonal pyramidal is a pyramid, and it is not flat. Trigonal planar is flat. Okay, and so things like nitrate, for example, are trigonal planar. Things like ammonia are trigonal pyramidal because nitrate only has 3 domains, so it's flat. Whereas something like ammonia has 4 electron domains, so it's not flat. Okay? All right, so just to clarify how the domains work, here's just a made-up example. When we are counting domains, we only look at the center atom. We don't look at anything else. And in this case, that's A. So around A, we have 4 locations that have electrons. Here's 1 bonding domain. Double bonds count as 1 domain, so do triple bonds. It's really just, domain means area, right? So this is 1 area where the electrons are at, if we're thinking about this from the perspective of A. This is another area. So that's a bonding domain as well, and this is a bonding domain as well. So A has 3 bonding domains. And it also has 1 non-bonding domain. So for the electron geometry, you would look at how many domains it has in total. Anything with 4 domains, the electron geometry is going to be tetrahedral, just like the example we just looked at in the simulation. It only has 3 bonding domains, so that means we're going to be having a trigonal planar and not a tetrahedral molecule. All right, so here's how you could use my diagram here. We have 4 total domains, so that means it's going to be listed in one of these 3 possible scenarios. If they were all bonding, we would have tetrahedral, so that's like the electron domain for anything with 4 domains around it. In our case, we have 3 that are bonding, 1 that's non-bonding, so the shape is going to be trigonal pyramidal. That's the molecular shape. In your VSEPR packet, you should copy this down. We learned that hybridization is sp3. We'll learn more about that later, but basically it means 1 s orbital and 3 p orbitals from the atoms have come together to form it. And so essentially, if you remember the order sp3d2, that's as high as it goes. If you remember that order, which is kind of rhythmic if you chant it enough, all you need to do is keep writing until you get as many orbitals involved in the hybridization as you have in your total domains. So 1s and 3 p's equals 4 orbitals. Down here, we have 5 orbitals, 1s, 3p, and 1d. Okay, and then down here we'll have 6. So that's how you figure out hybridization. And we'll notice that hybridizations are repeated. This is also related to electron geometry. All right? And again, we'll assume perfect bond angles, and then you can use these pictures to help you visualize what's happening. Okay, so that's the basic premise, and you're going to find as you do the VSEPR lab, you're going to learn which molecular shapes are the most common. Use this sheet, which is also in your lab, to help you. I don't expect you to memorize all of them, but eventually you should be able to recognize the main ones, which are going to be linear, trigonal planar, bent, very, very common, tetrahedral, trigonal pyramidal, and octahedral. Okay, so some of these we're not going to see very often, but the basics we do want to remember. Okay, so as a practice, let's try drawing these, all right? So first do your Lewis dot structure, and then figure out if you can tell the shape. Remember that Lewis dot structures do not give you the shape, because you could draw them in a whole lot of ways that are all equally valid. Okay? So you can pause the video, try it out, see what you get. So here's our ammonia that we were talking about. This has 4 total domains, 3 are bonding, so 1 is non-bonding. So our electron domain geometry is going to be tetrahedral because we have 4 total domains. And our molecular is going to be trigonal pyramidal. NH4 plus is what you get if you take another hydrogen and plop it right on. And so that structure is going to look like this. In this case, 4 total domains, all of them are bonding, so the electron and the molecular will be the same because there's no non-bonding electrons, and it's going to be a tetrahedron. P of 5, so P has 5 valence and F has 7. So we should end up with 40 electrons in this structure. P goes in the middle. You can arrange the F's in a whole variety of ways. Don't get too stressed out about it. They're all right. It's fine. So that's what we have. That means that our center atom of phosphorus has more than 8. It has to. The captions got it wrong. It has to have more than 8 is what I said, not 2 the number. All right. So then we're going to fill in the rest of the electrons. So far we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. Okay, so I ran out. I don't have to fit any more into the phosphorus. So now we're going to look at this phosphorus in the middle. We're ignoring all the unpaired electrons on the fluorines. They don't matter. We're just looking at the center atom. And we see 5 domains. We have 5 single bonds, so that's 5 domains. There are 0 non-bonding domains. So again, we're going to use the chart, right? So 5 domains might be any of these. Got 4 different options. The one that has no non-bonding is called trigonal bipyramidal. When you do your modeling, the trigonal bipyramidal shape, so when you have 5 domains, the trigonal bipyramidal shape is a tan model. So even though phosphorus is normally, we would probably use blue or purple, here we cannot. You have to use the tan one if you were making this, because there's 5 domains. So that's important to remember for your lab. The electron and molecular geometry are going to match in this case because there are no non-bonding electrons. Now, something important about trigonal bipyramidal shapes is that they are really symmetric, but not in the way you might expect. So I want to show you that. So in the VSEPR lab, we're looking at the symmetry of the whole molecule to determine whether something is polar or nonpolar as a molecule. So here is an example where I have actually changed the 2 fluorines on the top and the bottom of this to white. So the reason we call this a trigonal bipyramidal shape is because you have a triangle in the middle, so those 3 green atoms form the triangle, and then the pyramid part is to the bottom, you get 1 pyramid, and to the top you get the 2nd pyramid. So that's what trigonal bipyramidal means. Okay, and so a lot of the time people mistake this for not being symmetric because it seems like, so the bond angle between the top and the middle of the thing is 90 degrees, but the bond angle between your triangles is 120 degrees, so it seems like it shouldn't be symmetric. But it actually is. It has a lot of symmetry. So when you're doing symmetry, you have to cut the atoms along bonds. All right. So for our purposes, we're just going to cut them like right there. And as it turns out, you have 1 white, 1 green, and 1 white all in the same plane. So that's going to get all cut in half. And then you have 1 green on the right and 1 on the left. And you can do that anywhere in this molecule and get that same result. So it's always going to have 1 on each side. It's always going to be symmetric. If you cut it in half along the plane of the molecule, as long as the top and the bottom are identical atoms, this will be symmetric in that way as well. So one trick to telling if something is symmetric is I'll have students bring me their models and I'll say, is this symmetric? And they'll say, nah, trigonal bipyramidal doesn't look symmetric to me. And then I'll say, okay, close your eyes. Put it on the counter, close your eyes. And then I'll turn it. And they open their eyes and I say, can you tell the difference? And of course they can't. That means the atoms are symmetric. So when a molecule is symmetric, that means it's non-polar. All right, so we have 2 different kinds of polarity. One is talking about bonds and electronegativity. And if you calculated the polarity of this bond between phosphorus and fluorine, it's polar. It's a polar covalent bond. However, because we have the same kind of bond in all directions, and because this molecule is symmetric, the polarity of each bond is going to cancel each other out, which means this whole molecule is non-polar. Okay? Tetrahedrons are symmetric in the same way. As long as all the atoms on your tetrahedron are the same thing, then you're going to find that those angles cancel each other out. So this is really a vector problem if you're an engineering student. Right? All the vectors add up to 0 in the center, so that's non-polar. On the other hand, when we're talking about something with non-bonding electrons on the top, like our ammonia, right? Ammonia is not symmetric because you have these negative electrons along the top, actually. Remember how I said unbonded electrons take up more space? So my model kit has a way of showing that. So here's our unbonded electrons. Here's our hydrogens. And so you can see the top of this molecule is different from the bottom. this would be polar. Okay, and so you want to start to get a feeling for which geometries are polar and which geometries are non-polar, because that is the key thing in all of your future studies, especially in biology. Okay, I think you get the idea. I'm not going to do this one, although you are going to do similar ones in the lab. It's the same process. You add up your electrons. Anything extra goes in the middle. I'll just do it. It'll be easier that way. So Rn is a noble gas, and so it's going to have 8 valence electrons. And I know what you're thinking. You're thinking, I thought you said noble gases don't react. And normally they don't. But when you go farther down the group of noble gases, they're so big. Those electrons are so far from their nucleus that they can react a bit. And the chlorine will be 7 electrons each, and there's 4 of them, so 28 and 8 gives us 36 electrons. I'm going to change my color so we can differentiate it from the other. All right, and so if I have 36 electrons, normally we would want 8 times 5, which is 40. So we're going to have 4 electrons that are in bonds. Did I do that wrong? Okay. So we'll go Rn and connect it to each chlorine by a single bond. So we have to use 8 electrons to do that. Then we'll go back in and finish filling in our 36. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we have 36, but I only used 32. So the only place to put them, even though Rn already has an octet, I have to put them in the center. So that's 34, and that's 36. This structure would then have 6 domains, because we have, red ones are shown in bonding domains. We have 4 bonding. And I'm going to use blue to show non-bonding domains, so that would be this one. Each pair of unbonded electrons is a domain. So now we have 6 total. So our electronic config is going to be octahedral, because I have 6 total domains. And our molecular configuration is really interesting. This is called square planar. So essentially, you take your octahedron and you put the electrons on the top and the bottom, and you end up with a square. So when you're doing octahedral in your guys' kit, it's going to be a silver atom like that. So I'll build this and show it to you. Okay, so in this example, and again, you guys don't have the paddles to show the non-bonding electrons. You could just use a stick without an atom on the end of it. But in this case, you can see the octahedron with the 6 domains, which is the silver one. We put the atoms as far away from each other as they can get, so they will make a square. Okay, and then you have your non-bonding electrons, 2 on the top, 2 on the bottom. So this is also a really symmetric molecule. The electrons cancel each other, the bonds cancel each other, and so this would be non-polar. Okay, so that's how you're going to approach the lab. Hopefully this helps, but you should also use your professor's office hours when you're working on VSEPR. Make sure you come and see me or see your professor when you have the modeling kit, so I can walk you through the logic.